Today we're going to shift gears and start a topic called the radioactivity. Now, radioactivity involves the nucleus of an atom as opposed to the electrons that orbit around the atom. We've been talking since we started this unit about the discovery of the electron and then some of the properties of the electron, like charge to mass ratio and charge of the electron. We're shifting gears to that nucleus now, the part of the atom in which the electrons orbit around. Now, in order to talk about the nucleus of the atom and radioactivity, we need to be familiar with a term called an isotope and another notation called isotope notation. An isotope, you'll be familiar with this if you've taken chemistry. An isotope is a version of an element. It's a particular version of an element. Now, each element, like let's say carbon, nitrogen, uranium, silver, gold, each element has its own unique atomic number, its own unique number of protons. That element always has that number of protons. Carbon, for instance, has 6. Nitrogen has 7. Uranium has 92. I can't remember what gold and silver are, somewhere in the middle. They all have their own unique atomic number, and that doesn't change. Okay, if it isn't 6, it isn't carbon. If it isn't 7, it isn't nitrogen. If it isn't 92, it isn't uranium. But they can have different numbers of neutrons. So one version of carbon, for instance, might have 6 protons and 6 neutrons. Another one might have 6 protons and 8 neutrons. Another one might have 6 protons and 7 neutrons. Each different version of carbon or of nitrogen or of uranium or gold or whatever is an isotope of that element. Now, we're going to describe the properties of that isotope, of that version of the element, by isotope notation. And isotope notation would look something like this. We got 3 letters in the symbol A, Z, and X. X would be the element name. So for instance, if we were talking about carbon, we might make it a C. We would make it a C, in fact, if we were talking about carbon. Z is what we call the atomic number. And the atomic number is the number of protons. For carbon, that's 6, always. Doesn't matter what isotope or what version of carbon we have, the atomic number will always be 6. If you need to find that somewhere, check your periodic table. Okay, in the periodic table in your data book, there are 2 numbers. One's a small number, one's a big number. The small number is the atomic number, the number of protons, the smaller of the 2. A would correspond to the mass number. And the mass number is the number of protons plus the number of neutrons. This number can change depending upon the isotope of carbon. It may be 12. It may be 14. It may be 13. I'm going to make it 14. So for this particular isotope of carbon, we have 6 protons, and then we have 14 protons and neutrons combined. For any other isotope of carbon, we would have 6 protons and another different number of protons and neutrons combined. How many neutrons? If we got 14 protons and neutrons, how many neutrons would be present here? Yeah, 8. How do you know that? Good. If you have 6 protons and 14 neutrons and protons, then you're going to have 8 neutrons. Good. Now, sometimes you might see this notation written like this, just 14 carbon. We know that this is 14 protons and neutrons, but how do we know how many of them are protons? Quick, simple answer there. Andy, what is it? Carbon's always 6. We know that from our periodic table, right? Remember, it's the smallest number that appears on your periodic table. Check that number, you write it down, or just keep it in your head, and then go 14 minus 6 again, same as we just did. You might also see it written like this, although not usually. It means the same thing, right? Mass number of 14, atomic number of, check your periodic table, 6 in the case of carbon. I'm going to give you one example here. And if we're good with this, then we won't do any practice problems with this, okay? We got gold 197. We're going to find out how many neutrons are present in this gold 197. I'm going to ask you guys to do this one, even though it's an example. And I want you to find out not only how many neutrons we have, but how many protons we have, because that's what has to come first anyways. Okay, give you about 30 seconds to see what you can do with that. And then if you're good, as I say, we'll move on to the meat of today's lesson. So what's our answer here? How many protons present here? Kate, how many protons you got? 79 protons, good. How many protons and neutrons do we have? How many protons and neutrons combined? 197. How many neutrons? 118. It's going to be 197 minus 79, right? How many people got that? Okay, we're good then. This is not the end. Okay, this is a means to the end. This is a tool. It's like you're building a house. You got a nice shiny new hammer. Okay, the hammer is not the important part. The house is the important part. The hammer is only a tool to help us build the house. This is a tool that's going to help us with this next topic that we're going to do, which is radioactivity. We're going to spend a couple of days on this. Let's define it first. Radioactivity is a natural process. It's a random process in which one nucleus will decay into something else. So carbon might actually change into nitrogen, or uranium might actually change into thorium, or whatever the case may be. Now in chemistry, you don't really learn about that. You don't really learn about radioactivity. You learn about chemical reactions. In chemical reactions, carbon's always carbon, uranium's always uranium. But in nuclear reactions, including radioactivity, carbon can actually be changed to something else by switching up the number of protons present. If you go from 6 protons to 7 protons, it isn't carbon anymore. Or if you go from 92 protons to 90 protons, it isn't uranium anymore. It's a different element. And that's possible. We can do that via radioactivity. Now, we said radioactivity is a natural process. It's a random process. What do we mean by that? Well, by natural, we mean that it happens on its own. It's not us that does it. It's nature that does it. It's a random process. It happens when it wants to happen. We don't do it, we don't make it happen, and we don't control when it happens. Okay? It's completely outside of our control whatsoever. And you know what? Human beings don't like that. We like to control things. We don't control radioactivity whatsoever. It's a natural process, and it's a random process in which we produce not only a new element, but also radiation of some type, ionizing radiation of some type. What does ionizing mean? Let me ask another one first. What's an ion? If you've taken chemistry, you definitely know the answer to this. What's an ion? Okay, John. It's an atom that's gained or lost an electron. It's become a charged atom, basically, right? An ion is a charged atom, positive or negative. Chlorine -1, sodium +1, right? It's gained or lost an electron. Something that is ionizing radiation has the ability to turn atoms into ions. It has the ability to take electrons away or add electrons to something if it's ionizing. It's something that accomplishes the feat of turning an atom into an ion. Now, why is that a big deal? Well, sometimes it's not. But this radiation that's produced is sometimes harmful to us and to other living things because of its nature of being ionizing. Why? Well, if you start turning atoms inside our body into ions, then funny things start happening. Ions don't react the same way that atoms do. If you get ions floating around that aren't supposed to be there, then we start getting chemical reactions that aren't supposed to happen. And those chemical reactions might lead to things like sickness, radiation poisoning. Maybe we start puking. Okay, maybe we start bleeding out of our eyes and ears and every other orifice of your body. Okay, maybe we start getting cataracts. Maybe we develop cancer. Okay, maybe we have organ failure, acute organ failure. There's all kinds of things that can happen as a result of these chemical reactions. In the end, biology is really just chemical reactions, right? So when you get these funny chemical reactions happening, it changes our biology. And that's not usually a good thing because the biology of our body is usually pretty finely tuned to be correct already. Now, we're going to talk about 3 types of ionizing radiation. 3 types of radiation that's produced as a result of radioactivity that will cause atoms to become ions. The 3 types are alpha, beta, and gamma decay. Let's identify what these things are, first of all. Alpha decay occurs when you have big nuclei. And in that big nucleus, or big nuclei, you get too many protons. Why would you have too many protons? What's the big deal with too many protons? Well, there's 2 forces that act inside this nucleus. There's 3 actually, but we'll talk about 2 here, 2 relevant ones. 2 forces that are important. One is an electric force that acts between protons. Proton and proton, they repel each other. There's a repulsive force, and that force wants to break the nucleus apart. It's the homewrecker. Okay? It's the homewrecker force. Okay? It wants to break this nucleus apart. Okay? Obliterate this nucleus. The protons want to go apart and stay as far away from each other as possible. They don't really like each other. But then there's another force that's kind of the force that wants to keep them together, the mediating force. It's the counselor in the home. Okay? Things not getting along, well, let's have the counselor in here to kind of bring things back together. It's what we call the strong nuclear force. It's an attractive force. It acts actually between proton and proton. Protons actually attract each other by a strong nuclear force. It acts between protons and neutrons, and between neutrons and neutrons. If the attractive force is bigger than the repulsive force, it's all good. The nucleus stays together. The family stays together. But if the repulsive force is bigger, then watch out, because the nucleus is going to decay into something else. It's going to break apart. If you have too many protons, then what happens here is that the repulsive force becomes too big. Does that make sense? Too many protons, the repulsive force becomes too big. And if the repulsive force is too big, then we got to stabilize it somehow. We got to improve the ratio of protons to neutrons somehow. So what do we do in that case? We give off an alpha particle. The nucleus gives off an alpha particle. And an alpha particle, really all it is a helium nucleus. It's got 2 protons, 2 neutrons. It's just a helium nucleus. So now you still got a big nucleus, but it's a little bit smaller than it was before because there's this chunk of the nucleus that's gone now. This alpha particle, this helium nucleus that's gone somewhere else now. Sometimes you'll see an alpha particle written with this notation, 4,2 alpha. Sometimes you'll see it written with 4,2 helium. Okay, don't get bogged down with that. It's exactly the same thing. No difference. So whichever one you see, don't think, oh, I did it the other way. How do I do this? It's the exact same thing. It's got 2 protons, 2 neutrons. We're going to say the alpha particle breaks off to improve the neutron to proton ratio. Now, what's beta decay? Beta decay can occur in big or small nuclei. Beta decay occurs when you have too many neutrons. But this isn't a force argument, it's an energy argument. It's a stability argument based on energy. It's not that these forces are out of balance, it's that the nucleus is left in an energetically unfavorable state. It doesn't want to be in that state, so it's got to do something to be more energetically favorable. It's like a club. We're going to call it the nucleus club. Who's allowed to be a member of the nucleus club? Protons and, neutrons. Protons and neutrons, members of the nucleus club, right? Everything's going fine. Everybody in the club's getting along, and then one day, things are kind of out of whack a little bit. things aren't just quite normal. We're a little energetically unstable, unfavorable. So the guys in the club or the girls in the club, the protons and the neutrons in the club, they get together and they say, look, we got to do something about this. Otherwise, this club is going to be wrecked. Okay? Nobody's going to enjoy this club if we don't get a little bit more stabilized. And somebody stands up and says, you know what our problem is? You know what our problem is? Our problem is we have too many neutrons in this club. That's our problem. Somebody says, well, let's kick out some neutrons then. Everyone's like, no, we like neutrons. Neutrons are allowed to be here. We like neutrons. Why would we kick out neutrons? They're making us energetically unfavorable, but it's not their fault. We don't want to get rid of neutrons. We don't want to kick them out. Somebody else has a brilliant idea. He stands up and says, you know, if we were to change a neutron, if we were to physically change this neutron, into a proton, then look, we'd have one less neutron and we'd have one more proton. That would change the balance, wouldn't it? Everybody's going to be happy now, right? Everybody says, yeah, that's a great idea. And then somebody stands up and says, yeah, but wait a second. We can't do that because it's going to violate the law of conservation of charge. We got a neutral particle here, changing it into a positive particle. You can't do that. And then the first guy stands up and says, yeah, well, what if we make an electron too? What if we make a proton and an electron? The other guy says, hey, that might work. So they do that. They pick the neutron, the last neutron to join the club, say, look, we're going to change it into a proton and an electron. So they do it. Hey, we're more favorable energy state now, right? Because we got one less neutron, we got one more proton. We don't have too many neutrons now. But wait a second, there's an electron here. There's an electron here. Electrons aren't welcome in this club. Get out. Get out, electron. We don't want you here. So the electron leaves. That's the beta particle. The electron is the beta particle that leaves. We can call it 0 minus 1 beta, or we can call it 0 minus 1 E. Same deal. You get too many neutrons, you change a neutron into a proton and an electron, but the electrons can't stay because they're not part of the club. So they leave. They're shamed out of the club. We've improved the ratio here now. We don't have as many protons. We got more don't have as many neutrons. We got more protons. So we're better. We're in better shape here now. Maybe we're still not quite stable. Maybe we got to do something else, but we're closer to being stable at least. Now, there's actually another kind of beta decay as well. A subcategory. Here, let's do this in a different color here. A couple subcategories of beta decay. Sometimes you got too many protons. And sometimes the solution to too many protons is to break off an alpha particle, but sometimes the solution to too many protons is to do this little trick that we just did. Change it. Change a proton. What do you think we're going to change a proton into? You get too many protons? Let's get rid of one. Change it into a neutron. Hey, that improves the balance, right? If you had too many protons in the club, change it into a neutron. But that's not quite working here, right? Because we got positive changing to neutral. So what else we got to make? A neutron and an electron, because that would be negative on the right side, right? Positive and negative. A neutron and, does anybody know what this is? It's a positron. It's an antiparticle of an electron. It's antimatter. How many people have read the book Angels and Demons or watched the movie Angels and Demons? Talk about antimatter there, right? And there's some bad science in there, but there's some good science as well. In the end, you guys, part that everybody remembers from the book, matter and antimatter come together, they annihilate and they produce pure energy. That's true, they do. Okay. Antimatter is exactly the same as matter except for one thing. There's always one difference, always one property that's different. In the case of electrons and positrons, The difference is the charge. Identical in every way. Mass, every way. Identical except that a positron is positive and the electron is negative. It's not a proton, because protons are heavier than electrons. Positrons aren't. They're just positive. That's beta plus decay, we call it. That's producing not a proton that gets kicked out because it's not really welcome in the club. That's producing a positron. And finally, gamma. Gamma is just electromagnetic radiation. No protons, no neutrons, no positrons, no electrons, no nothing. It's just radiation. Remember on the second day of our EMR unit, we said radio waves and microwaves are produced by oscillating electric charge. We said that X-rays were produced by rapid deceleration of electrons. We said that gamma rays were produced by nuclear decay. Isn't that what we're talking about? The production of gamma rays by nuclear decay. This happens as a byproduct of something else, because kind of as an afterthought of something else. We'll say a byproduct of above. So after a neutron has been changed into a proton and an electron, the nucleus is left in an excited state. Think about that. Guys, listen, you've just witnessed a neutron changing into a proton and an electron. You'd be excited too. The nucleus is excited, but it doesn't want to stay there. The nucleus is kind of like Eeyore. I don't want to be excited. I want to go back to my regular state. So as it goes back to its regular state, it gives off a gamma ray. Right? It wants to be Eeyore. It doesn't want to be excited. It gives off a gamma ray. Gives off a gamma ray to return to an unexcited state. And all is good in the atom. Now, we're going to talk real quickly here about two properties of each of these types of radiation. The first property is going to be ionizing potential. The ability to ionize atoms. They all can ionize atoms, but some are better than others. The second one that we're going to talk about is the penetrating potential, or the penetrating power. They all have the ability to go through matter. Some of them go through matter better than others. Okay, we're going to compare the ionizing potential and the penetrating power of all, we'll call it all three types of radiation here. Because in the end, whether we're talking about beta negative or beta positive, it's the same deal then. Alpha particles have a very, very high ability to ionize matter, to ionize atoms. This is not something that you want to mess with. Okay? They have the ability to ionize atoms to a very, very high degree, which means that you can change lots of atoms into ions and then crazy things start happening. Crazy chemical reactions that aren't supposed to happen start happening. Gamma rays, I don't want to say that they have a low ionizing potential, but it's the lowest of the three. And beta particles, beta negative, beta positive, it's medium. So there's somewhere in between. The penetrating power, on the other hand, is exactly inversely related to ionizing potential. Alpha particles have a very high ionizing potential, but they have a very low ability to penetrate matter. In fact, listen, someday you get mad, you're just done with physics 30, and you decide you're going to bring an alpha particle gun this alpha particle gun you've invented into school, and you're going to get your physics teacher. You come into this room and you say, I've had enough. I've had enough of you. And then you go to shoot me with your alpha particle gun. And what do? This. I hold up a piece of paper in front of me, and that's my shield. Alpha particles have such a low penetrating power that 1 or 2 sheets of paper literally will shield you from alpha particles. It's incredibly low penetrating power. Okay, my clothes would shield me from alpha particles. A couple sheets of paper would shield me from alpha particles. The penetrating power is very, very low. Gamma rays, on the other hand, although they have a low ionizing potential, they have a very high ability to penetrate matter. Gamma rays will go straight through your body. That's why we use them for cancer treatment. Radiation therapy and cancer treatment is gamma rays because they have the ability to penetrate matter really, really well. They'll go straight through your body. You'll need several centimeters of lead to protect you from gamma rays, lead or concrete. Okay? Hold up a couple sheets of paper with gamma rays, it's not even going to blink. It goes right through it. It goes right through your body. Of course it's going to go through a few sheets of paper. Beta particles, they're kind of the fence sitters, right? We kind of ionize matter. Yeah, kind of. We're in the middle. Yeah, we kind of have a low penetrating power, kind of high though, kind of in the middle. It's maybe a couple centimeters of flesh, human flesh. So beta particles could certainly get into you further than alpha particles, but certainly not like gamma rays. So there's a flip side to everything, right? You got a high ionizing potential, you got a low penetrating power. You got a low penetrating power, you got a high ionizing potential. Make sense?